Hi, today we're going to look at tangent line approximations, one of the more unique and neat applications of the derivative, I think, because it allows us to approximate close values. For example, now we're going to be using 1 plus sine of x later on, but let's say we want to find the sine of 1 plus the sine of 1.5. Well, the problem is without a calculator, I really don't know that value, but I can approximate it by letting it be the sine of 0, because I know the sine of 0 is 0, so I can approximate my value as 1. Now, what we're going to find out is tangent lines allow us to get much closer, and here's how they kind of work. Let's graph the sine function from 0 to pi. We know it looks like this. Now, at 0.15, I have a value. That's my actual value. I don't know what it is. It's unknown. But what we can do is use a known value to approximate it. And here's how we do that. We don't know the sine of 0.15, but we use the sine of 0. So at 0, what we're going to do, we're going to draw our tangent line. And there it is. Now, the tangent line, it doesn't give me the exact value, but it gets me pretty darn close. It gives me an approximate value. And we're going to find out just how accurate this is. And it's really kind of neat. You're going to find out. So that's the whole idea of what we're going to be doing here. So what we have to kind of find is, one, we have to find a couple things. One, we have what's called the actual function, the actual value. Now the actual value itself comes from the function. And then we have what's called the approximate value. That's going to come from the derivative, or the tangent line. And these become really big for us when we start talking more about differentials. So how can we use this in order to get a better accurate reading of the sine of 0.15? Well, very simple. What we're going to do is we're going to pick a known x value close. We don't want to pick something far. Hey, look, I know the sine of pi, but watch what happens if I draw the tangent line. Wow, look at that approximate value. It's way off. That's too far off. It's huge off. That's bigger than Mr. Warnell's nose off. So what we're going to do is we're going to pick one that we know is close. Now, some people say pi over 12. Yes, that's very close too, but not everyone knows the value, so I pick 0. Now, so we want the close. That's the key word. So we know the sine of 0. So therefore, I'm going to let x be 0. I pick an x value, a known value. Next, I write my tangent line. Well, we know how to write a tangent line. We need a point. X is 0. I need to find the y value, f of 0. I get that from the original function, 1 plus sine of 0. We get 1, so we get the point 0, 1. Next, we need to get our slope. Well, the slope comes from the derivative. That's just going to become cosine of x. And the derivative at 0 is just 1. So therefore, our slope is 1. Write your tangent line. Y minus 1 equals, that's ugly looking 1. Y minus 1 equals 1x minus 0. Now, we like this format later on because guess what? That's going to be our error in y, and that's going to be our error in x. We're going to talk a lot about that when we get to differentials. And understanding this really will help us out quite a bit. Next, we use the tangent line to approximate the value. So here's what we do. So I know y minus 1 equals 1x minus 0, and now I let x equal 0.15, and I just plug it in. Y minus 1 equals 1.15 minus 0, and if you solve, you get about, it's approximation, 1.15. Much closer. Now, let's calculate the actual value, though. Sorry, before we do anything else, let's calculate the actual value. I'm going to use my calculator for that. That is 1 plus the sine of 0.15. And that is equal to 1 plus the sine, 0.15, and 1 plus the sine of 0.15, there we go. And I get 1.14944. Wow! Look how close that was. Look, our original guess was just 1. That's using elementary school approximations. But by using the tangent line, look how much closer we are. And how close are we? Well, that's our error. Now to get the error, we're going to take our actual value minus our approximate value. and we take the absolute value of that. I can't spell error today. To get the error, it's the actual value of 1.1494 minus the 1.15. And if you type that in your calculator, 1.1494 minus 1.15, we get, whoa, negative 6 times 10 to the negative 4. That is tiny. Look at that. What is that point? And we take the absolute value of that, of course, we get 0.0006. Look, let's count this. Tens, hundreds, thousands, tens, that's 6 10,000ths off from the actual value. That's how accurate tangent line approximation is. But be careful, the key word, you want to pick a close value. Okay? So let's take a look at the back page here, the rest of it, how else we can use this. Now, here we have something. Oh, we forgot to answer one more thing. It asks us about this idea of concavity. Well, if you look at the graph is concave down. My tangent line, therefore, is going to be above it. No matter how I try to draw my tangent line, it's always going to be above it. Well, that's telling us something about a relationship between the approximate and the actual value. So let's come back up here, and we're going to talk real quickly about concavity before we move on. Now, as far as concavity goes, here's what the rule says. If the actual value is less than our approximate value, the function is concave down. Then f of x is concave down. Now, this is easy to see if you sketch it. Ready? If I draw my tangent line, and my actual value, that's the curvy thing, that's the function, it's going to have a curve to it, it's less than my approximate. Remember, the tangent line is my approximate value. So if it's my actual below it, the only way I can draw it is like this. So it must be concave down. And likewise, if the actual value is greater than the approximate value, then the function f of x is concave up. And likewise, if I draw my tangent line, there's my tangent line, my actual value, the curvy thing, has to be bigger than, it has to be above my approximate. Remember, the tangent line, that's your approximate value. It has to be above it. So there we go. It must be concave up. So down here, when I want to talk about concavity, I'm going to compare my actual value and my approximate value. I'm just going to compare them. Well, my actual value was 1.149. My approximate was 1.15. So my actual is actually less than my approximate. Therefore, f of x is concave down. Now, you can memorize that. I don't. Quickly, what I do is I just draw it. I draw my tangent line. My actual is less than it. It has to be below. I draw a function, and it turns out to be concave down. Very easy to do. All right, next. Now, let's talk about the back page here. How else can we use this? Well, it gives us some information here. It gives us the point, 3,2. So I'm going to write that down. There's my point, 3,2. Gives me the derivative. The derivative gives me slope. So the slope is negative 3. And now it's giving me concavity. And this is telling me that the function here is going to be concave up. So I draw it. Concave up. I draw it out. I don't know how that's going to help me, but it may help me. I list out all the information and how it can help me. It doesn't take long. Next, it says use a linear approximation, keyword linear, to approximate these values. Well, I need a point, which they give me, and a slope, which they also give me. So I got my tangent line. Y minus 2 equals negative 3, x minus 3. There is my tangent line. So if I want to estimate f of 2.9, I think, Mr. Werner, we don't know what the function is. We don't have to. We're approximating it. Now, also what I want you to look at, my known values are at 3. I'm at 2.9. Notice, we're not far away. We're close to 3. This won't work for values far away. Remember, calculus is the study of tiny distances. Itty-bitty tiny. Okay? So very tiny. So I'm just going to plug that in. Y minus 2, negative 3, 2.9 minus 3. Y minus 2 equals negative 3. This becomes negative 0.1. And if you solve it, we get y is about 2.3. The smaller the error here, the smaller the error here. Okay? And we're going to talk more about that on when we get the differentials, how we minimize error. So if I want to try 3.1, same thing, y minus 2, negative 3, 3.1 minus 3, and I get y minus 2 equals negative 3 times 0.1, and we get y is about about 1.7, positive 1.7. There we go. Messed up on my arithmetic in my head. Positive 1.7. Now the next question, it says, is our estimate too large or too small? Well, that's dealing with concavity, because that's dealing with, is it an overestimate or an underestimate? And if we move back here to the other side very quickly, if it's hello, let me focus here real quick. Okay, if it's concave down, notice my tangent line is above the function. This is an overestimate. And over here, where my tangent line is below it, below the function, this is an underestimate. So another way to look at it, if it's concave down, it's an overestimate. If it's concave up, it's an underestimate. Trust me, draw these, it will help you. So if I come back over here, and I want to know if my too large or too small, I look at the concavity. Well, remember, we know it's concave up. So draw a tangent line anywhere you want to. No matter where I draw the tangent line, it's going to be below. The tangent line is below the function. Always, no matter what. No matter where you place it, it's always going to be below. And since my tangent line is my approximate, we're saying that my approximate is below the actual value. Because remember, this is the actual, and this is my approximate. My approximate value is less than the actual. So what we can say is, because f of x is concave up at x equals 3, we know this is an we know our estimates are too small. And that is because they are underestimates. Very easy to do. Okay? Now next they say graph a possible function. That's pretty easy to do. Graph the point first. 3, 2. We know it's a negative slope, and we know it's concave up. So what I'm going to do now is it's going to be like a parabola, obviously, or some people draw natural exponentials, but we can draw this as a parabola. Now be careful, it's not my vertex. It goes down, has to go below it before it goes back up. So that could be a possible function. All right, so practice these, okay? I'll see you guys in class, and I'll look over some differentials. Bye.